Well, you can use it to find the maximum min, but it's the slope. So for any given graph, and for any given function, so this is my function f of x, if we consider any given point, we'll just call a point A, right? Then if we look at f of A, then that's telling us the y coordinate. So there's f of A. So my input was A, there's my y coordinate. I can look at that coordinate, I can call it A, comma, f of A. So that's what the function is telling us, is the y coordinate. And then if I consider the f prime, okay, so f prime of x, which is a completely separate function that we derived from f of x, then f prime of x is going to tell us the slope at that point. And then that slope right there is equal to f prime of x. So how does that look? Does that drawing make sense as a nice condensed summary of what we've seen so far? You're considering some point of the function, well, some input value. You look at the function of that value. The f of a tells you the y coordinate, which is right there. So you get the x coordinate, y coordinate. And then if you want to know the tangential slope at that point, the slope is equal to f prime, the formula that we derived where you input the value of a. So f of a tells you how tall that point is. F prime of a tells you the slope at that point. And that's what we know so far. Okay. In calculus, things get blank before they get blank. They get worse before they get better, absolutely. What is the formal algebraic definition of the derivative? So what is the formal definition of the derivative? The derivative is, what's the definition? Well, what do I write even before that?
Oh, the limit.
Yeah, the limit as h approaches 0. And then keep going, Sarah. F of x plus h and minus f of x all over h. And this whole formula right here means something. You could give a complete English sentence about this. You could say, this right here is the secant slope. This is the secant slope between 2 points. Really, between 2 points. This is the secant slope between 2 points. And then what are we going to do to those 2 points? Move them infinitely close together. So that's what this derivative formula does for us. It considers the secant slope between 2 points. Then you allow the distance between those two points to become 0, which means they get infinitely close. And therefore, this becomes the tangent slope at 1 point. Yeah, so this is a very powerful statement. So hold on, I should put something right here that says, bring the 2 points infinitely close together. Bring 2 points infinitely close. There, and so that's the whole meaning behind the formula right there. Okay, what does that formal algebraic mean? Oh, what does that definition mean? Well, okay, I just said it. That's what it means. It means you're finding the slope between 2 points, you bring those 2 points infinitely close together, and it becomes the slope at 1 point. Interesting, you have to read it from right to left. And in order to find the slope of a curve at a single point, we found the slope between 2 points, and you bring them infinitely close together. That's the whole idea. Okay, well, let's see where we're at. Today is February 5th. We're going to wrap up section 2.4 and then move into 2.5. We have 2 days to do 2.5. And then on next week, on Tuesday, you get to take your first test. Very exciting, wasn't it?
I have a question regarding 2.2.
Yes.
Will that do today or the 29th? I believe you said 2.2 and 2.2.
If I said that, I will make it so. What did the due dates on the system do? Or what it is?
29th.
On the 29th?
Yeah.
I can extend it if that's what I meant to do.
2.3 is to be completed next week.
Next week.
Yeah, okay, so 2.3 is due next week? No, but we finished 2.3 last week. So 2.3 should be due today. Because we're definitely on 2.4 right now. So definitely as of today, everything should be due from 2.2, 2.3. So 2.2 and 2.3 should both be due today. I believe. Yeah.
I have it here in 2.3 until the 12th.
Oh, well, yeah, 2.3 is due on the 12th. Oh, well then I was nice and I gave an extended due date. I don't know why I did that, but I'll keep it that way. So you have until the 12th.
So 2.3 is due next week.
Yep, apparently. If that's what it says. If that's what it says, I'm not gonna, make it sooner.
So what about
Does that answer your question?
So what about 2-2?
2-2 should definitely be due. 2-2, yeah. Oh, you couldn't do it? Okay, well, I tell you what, as soon as we have break, I will go back and fix all those due dates. So here, let me just make a little note to myself. I'll do it during break. Fix dates. Okay, so, Rosa, will that?
Yeah.
Okay, I'll go back and fix all those. I'm sorry that got confused.
Yeah, because I mean, I have some missing in 2.2 topic.
Okay, and no matter what, you can always use a late pass to extend the due date. And or if a section is closed, you can email me and I'll open it back up to you if you just have questions today. Okay, so that's where we're gonna work on today. Oh geez, I already told you both of those jokes. Let me see if I can scan ahead and find a new joke for you. No, that's the same joke. We'll go forward with more. Why did the chicken cross the road? Okay, I'll tell this one. Why did the chicken cross the road? To get to your house. Knock, knock. The chicken! So this combo joke, okay. All right, so here we go, folks. Let's look at where we were on 2-4. Where did we get to? We did number 1 and number 2, and we got to number 3. And yeah, I think that's where we left. We stopped at number 3, and it said, what was the cost of the 4,500 first item? And we all agreed that to find the cost of that exact item, you would have to do the cost of all 4,501 items, and then subtract out the cost of the first 4,500 items. And if you consider that difference, that's going to be giving you the cost of just the 4,501st item. So does that make sense? All right, and I think we finished that? Okay, so moving on. The demand for a product is given by the following demand function. Now let's take a moment to really talk about that function right there. First of all, everybody make a quick sketch. What we have here, this is mx plus b, mx plus b. And so just by looking at it, we know our y-intercept is at 88, and we know the slope is negative. So what we're going to do is just make a quick sketch, just make a little graph where you have a y-intercept of 88, and then give it a negative slope. So sometimes our graphs don't have to be overwhelmingly precise. They just have to communicate the main idea of what's happening in the graph. So that's what we know for sure. And so now, what does this mean? Let's take a look. Q is the input. All right, so therefore that's the x-axis. And what does Q represent? Q is units in demand. So Q always represents quantity. Yeah, Q always represents quantity. And that's either quantity sold or quantity purchased or quantity manufactured. So that's Q. And then it says D of Q, okay, so the function itself, which is the output, D of Q is the price per item. So that's interesting. D of Q is representing the price that the item can be sold for. So this whole thing right here that's being computed right here, you're computing the price that you should sell the item for. So that goes up on the y-axis. This is the price in dollars. Now let's consider the example they're giving us. Okay, so what is a demand function really saying? A demand function, I like to say, is a little bit like if you could know the mind of God regarding a society and what people will do and what people would buy in a given situation. It's kind of make-believe that anybody would really know this information, but it's like the assumption that if you know the market well enough that you can have an idea of what people will do. And what they're saying is here that if 10,000 units are in demand, meaning that you want 10,000 people to come out today and go to a store and buy your product, right? You want 10,000 people to come out. Then what price should you charge? So let's find out. First of all, 10,000, do we plug that into the function or do we set it equal to the function? Yeah, we plug it in. How do we know we plug it in? Because it's units, that's quantity, therefore it's the input. So we take our demand function, we're saying if I plug in 10,000, then it's going to be negative 0.007 times 10,000. And of course you can just do this on your calculator, there's no need to write the whole thing out. Isn't that interesting? I'm telling you that it's okay that you don't write this out. You could just plug it into your calculator. This is very rare for me to say that you don't have to show work. But I mean, in something like this, you're just plugging it in, right? So 10,000, we'd have to move the decimal quite a few times. 1, 2, 3, 4. Is that negative 70 plus 88? And so that's 18. Now, what does that mean? 18 is the price, right? So I'm going to come up here, I'm going to find my point on the graph, and now that's 18. Now you'll notice that my graph is not terribly to scale, right? 18 seems close to 88. Probably my 10,000 should have been more over here. But again, it's okay that the graph is not to scale. I'll fix it just for the sake of, looking at it there. Does that look better? If I put it there, that's a little more realistic where 18 should be and where 10,000 is. Okay. So now I have a coordinate 10,000, comma 18. Now the discussion that I want to have with you about this is, again, this is like if somehow you had special insight over the society of people who live in your community. And what you're saying is that if I charge $18 per item, exactly 10,000 people will show up to buy it. No more, no less. Not 9,000 people, not 10,005 people. Oh no. If I charge $18, I have the mind of God to know that exactly 10,000 people will come out. Okay? That's kind of what you're pretending when you talk about a demand function. You're pretending to have special insight. So what would happen if I charged $20? What would happen to the number of people who showed up? There'd be less people. Now, does that make sense? You just raise the cost of your product. And they're like, I was willing to pay 18, but not 20. All right, so less people showed up. They stayed home. Whereas what would happen if I charged less money? What if I only charged $15? More people would show up, maybe 11,000. Okay? So this demand function somehow has its finger on the pulse of your community. That you can say, hey, if I charge 18, this is how many people will show up. But if I charge 20, fewer people will show up. And if I charge 15, more people will show up. Okay? So that's what the demand function is really saying. When we say that if you input the number of people you want to sell the product to, the output will be the price, the magical price, that if you use that price, that many people will actually show up. Okay, so for the duration of this class, we're going to talk about these demand functions as though they have this magical quality, that you know how many people will show up. Okay? Any questions about that? Just the word itself, demand function. Demand. Does that sound like we're talking about price? It sounds kind of funny. Shouldn't it be called the price function? Yeah, that would sound a lot better, wouldn't it? It might sound better if it was like P of Q. And then now if the input is how many people you want to show up, then this is the price that you should charge. But unfortunately, it's called the demand function. And it's called D of Q. So we always have to stare at the D of Q for a second and be like, wait a minute, demand. What are we really talking about? That's the price of the item. That's the price that if you charge it, they will come. Okay? All right, same thing goes for the supply function. The demand and the supply function are both having this magical quality that you're claiming to know what a group of people will do. Okay, let's move on to number 6. The demand equation for an item currently being marketed is given by D of Q equals all that. So again, what is this demand function telling us, really?
You skipped 5.
You know what's funny, guys? I didn't see 5 on my... Oh, there it is. Okay. And let's do 5. I might have had a reason for putting 6 first, but yeah, can we do that? Can we go to 6 first? Yeah, because I might have had a reason. I might not have had a reason, but I might have had a reason. So the demand equation for an item currently being marketed is given by D of Q equals negative 0.15 Q squared plus 44. And again, I always find it helpful, myself personally. I'm not just telling you to do it because I think, oh, you guys have to do this. I do it, okay? This is what I do. I always label what my units are. So Q again is my quantity, and then D is actually the price I should set. Price I should use. Right? That's there. That's what the demand function is representing. And that's what this thing is equaling. That's the price I should use. Okay, so D of Q is, again, the dollars that can be charged per unit. Q is thousands of units. See, this time it's quantity in thousands. So that's important. If you input the number 5, what are we really saying? 5,000 units. Okay. For example, Q equals 18 means 18,000 units can be sold. Okay, so if 14,000 units are to be sold, meaning you have a warehouse, right? Here's your warehouse. Warehouse. What do you keep in the warehouse? Wares. It's a house for wares, right? So you keep all of your wares there, and you have 14,000 units inside, and you want to get rid of them, right? You want to get rid of them, but you also want everybody to be happy. So for instance, at the end of the month, you don't want to have 1,000 units left over, because then you have to continue paying rent on the warehouse. So you want to be sold out, but you don't want to be super sold out that people are showing up saying, I want to buy one, and you're like, sorry, I'm all sold out. And then they go out on the street and talk bad about you. Like, that company's no good, they always run out, right? So that's why you need this demand function to set the price just right so that you're gonna have 14,000 people show up and no more, right? If fewer than 14,000 people show up, you're gonna have overstock, it's gonna gather dust, you're gonna have to pay rent for this warehouse that you don't want to. If more than 14,000 people show up, you're gonna have unhappy customers. So that's why we use the demand function to know that exactly the amount of people are going to show up to buy exactly the amount of quantity that you have. So if 14,000 units are to be sold, what price should be set? What do we do? Yeah, you just plug in 14, right? If you plug in 14, you're going to get negative 0.15, 14 squared, plus 44, and then you use your calculator. And this is telling you the magical price, that if you charge this price, then exactly that many people are going to show up. And I got $14.60. Is that what you got from your calculation? 1460? Yeah. So what would happen if you were a little greedy and you're like, hey, I'm going to charge $15? Would 14,000 people show up? No, some people are going to be like, forget you. I'm not paying 15. I was willing to pay 1460, but I'm not willing to pay 15. So how many people would show up? Yeah, like 13,500, or you know, who knows? And then maybe you're like, hey, I'm feeling kind and generous. I'm only going to charge 14. You know, I'm gonna give a little discount. Yeah.
Well, since it's like a parabola though.
Yeah.
Like, doesn't that mean also like the same number? Like at that price, there's also like some other kind of radical number that it would hit. I'm not sure.
I'm not sure what you're saying, because if you're aiming to sell a certain quantity, which is like 14, then there's only going to be one price.
Okay.
But then you're saying that over here you could sell 16,000
It'll be the same
at the same price. That's a really interesting idea. Let's consider the function that they just gave us and graph it and check to see if that's a possibility. What's the function called? Or what is it? Negative. Yeah. Now, does everyone appreciate what Henry just brought up as an example? He's saying, uh-oh, for a given quantity, couldn't there be two? And so, in this particular case, what's the answer?
No.
No. Because in order to get those two symmetric prices, you know, one price that has two different quantities, the other quantity would be a negative. So, but you're right, like, what if all of a sudden the function was actually shifted to the right? Then that would be a real conundrum. That if you charged $40, either, you know, 5,000 people would show up or 15,000 people would show up. That would be weird. Yeah, so very good point, Henry. I'm pretty sure that no demand equation will act that way. Furthermore, demand equations, if you take a economy class, economics class, demand equations are always going straight down. Because after all, if you charge, let's say that you're right here, and that's, you know, 10,000 people, then if you lower the price, okay, if you lower the price, more people will show up. I mean, that's almost like a law of nature. If you lower the price, more people will show up. Anyway, that could be a much longer philosophical discussion about economics and supply and demand curves, but in this particular case, we're safe. Okay, good question. Okay, so that's it, right? So I don't think we answered my question. What if you were kind and you lowered the price? Yeah, too many people would show up. You'd have people knocking on the door after you already sold out. And you'd be like, sorry, I already sold out. And then they'd go away disappointed. And that's what they're going to remember about your company, disappointment. Yeah, terrible, right? Okay, wonderful. So that's just another nice example of a demand equation. Let's take a look now at 5. So sorry to make me skip around here. 5. It says, suppose your demand function is given by that. Now, given what Henry just said, we have to really be curious. I wonder what that parabola looks like, because that particular parabola is a parabola and it is facing down. Where Q is thousands of units, so this is in thousands, and D of Q is just in regular dollars, so not hundreds of dollars or anything like that, just normal dollars. Compute the following. So what should we do first? And the fact that I'm walking over here tells you. What should we do first? Yeah, I mean, graphing the function first is always a good idea, so that you know what you're talking about. And we all want to know what we're talking about. So negative x squared minus 2x plus 596. And go. Let me fix my window. So my x-axis is 0 to, we'll just say 10. Okay, maybe 50. Okay, maybe 12. Okay, there we go. So we have a nice demand function. Henry, does your situation happen? No, because the rest of the parabola is over here on the left. So again, demand is strictly decreasing. That's what our function looks like. You all might as well draw a picture of that. And then we can have a discussion about what this demand function is telling us. So if you want to, put the vertex of the parabola over here, and then it's going down. So there's our function, and it says if 14,000 units are to be sold, what price should be charged? So we've already seen a problem like this. This is pretty straightforward. Again, 14,000 is really Q equals 14. So we would just say D of Q equals negative Q squared minus 2Q plus 596. Have we already talked about the value of writing a function empty? Yeah. Yes, I wrote my function empty. Now I'm ready to go ahead and plug in all my numbers. So I'm going to plug in 14. And then again, you'll just take out your calculator and calculate all that. There's no need to do it by hand. So negative 14 squared minus 2 times 14 plus 596. Did anyone else get 372? So let's remember again what that means. If you charge, $372, 14,000 people will show up. It is a lot of people. I mean, what on earth is this product even? What would you pay $372 for? Like a cat? Okay, yeah, a cat. Maybe like a really small iPod. I don't know how much iPods and iPhones, not iPhones, but iPads go for these days. It could be a small tablet, right? Who knows?
A TV.
Or what? Oh, a TV? Yeah, there you go, a TV. Okay, now keep in mind you can write it the other way around as well. You can say, if you want 14,000 people to show up, then you need to charge $372. So the logic goes both ways. Okay, if a price of $497 is set for this item, how many units can you expect to sell? And this is the really cool part, where again, you have the mind of an all-knowing being. And you're like, hey, if I charge $497, how many people will show up? So how do we do that? Do we plug 497 in or set it equal to the function? We set it equal to the function. So I'm going to take my D of Q equals negative Q squared minus 2Q plus 596, set it equal to 497. And at this point, we are reminded that we are in a class called Business Calculus, subtitled Advanced Algebraic Techniques for Cancellation and Manipulation, which basically means you need to remember all the algebra you've ever done in your life. So we want to solve this equation. What do we need to do to solve a quadratic? There are a lot of ways to solve a quadratic. Like let's just say I gave you the quadratic x squared minus 7x plus 12 equals 0. And 2 ways to solve that equation. You can factor or Google it, is that what you said? I suppose if you move the 12, you can start completing the square, if you like completing the square. So you can factor, you complete the square, or you could quadratic formula, right? Or you can just graph it and find the x-intercept, because the solution to any equation set equal to 0 is just the x-intercept. Okay, so we want to solve this thing. If it was me, I'd start by bringing the 497 over to see what I'm really dealing with, to see if it's even factorable. So we have negative q squared minus 2q plus 99 equals 0. Myself personally, I don't like that the leading term is negative, so I'm going to multiply the whole equation, both sides, by negative 1. That way I can change all the signs to q squared plus 2q minus 99 equals 0. And my first thought is always to see if I can factor, because if I can factor, it's easier, I think, than doing the quadratic formula. So what multiplies to make 99 that adds to make 2? What's one of the only things that multiply to make 99?
99.
Well, 99 times 1. That won't add to make 2, or subtract to make 2. Yeah, 9 times 11. And 9 times 11 has a difference of 2. So that's what we're looking for. If it's going to be multiplying to make 99, that means it has to be 9 times 11, and one of them has to be negative, and one of them has to be positive. So, and since we want them to add up to 2, it would have to be a positive 11 and a negative 9. Does everyone agree with my factor table here? I want two numbers that multiply to make negative 99, so one is plus, one is minus. And when I add them, I want to get positive 2. So there we have it. We have q minus 9 times q plus 11. And now, by the zero product rule, we have something times something equals 0. And the only way that would happen is if one of them is equal to 0. So you say either that's equal to 0 or that's equal to 0. I'm just going to push up a little bit. So either q minus 9 is equal to 0 or q plus 11 is equal to 0. Which means q must be 9 or q must be negative 11. Notice, Henry, that your situation came through in the algebra because they're suggesting that that price would happen if you either let the quantity be 9,000 or let the quantity be negative 11,000. So that's that ridiculous scenario right there. And the algebra showed it to us. Okay, so the answer is, if you set the price at 497, how many people will show up? 9,000 people. Or negative 11,000 people. This solution is called extraneous. Extraneous means the algebra told it to us, but it makes no sense in the context of a word problem.
How many units?
You expect to sell 9,000 units. Well, that's true. We're not selling people. Yeah, that's a good point, Moza. We should say 9,000 units. I always think about it in terms of how many people are going to show up at my door. Henry?
So like in the last one, we have like 72, that's like dollars per item.
Yeah.
Unit.
Yeah.
It's not dollar per 1,000 units, it's dollar per regular.
It's price per item. So going back to the original, I don't know that this problem even defines it anymore. There was a couple problems ago where they defined the demand function, and the demand function is price per item. Not per thousand.
Q is in thousands.
Doesn't matter if Q's in thousands, the price is still price per item. Yeah, good question. Yeah, it's still price per item. Okay, wonderful. At what value of Q does D of Q cross the Q axis? At what value of Q does D of Q cross the Q axis? So what point are they asking for? Yeah, they're asking for the intercept, the actual intercept. So how do we find that out? We're saying when does the function equal what? Yeah, when does the function equal 0? So now we're saying negative q squared minus 2q plus 596. When does that equal 0? Now how do we know that's what we're asking for? Well, because if you're at the x-intercept, your x value could be something, but what does your y value have to be? 0. So again, this is your input and this is your output. So we're saying that the output has to equal 0. So we're saying the output has to equal 0. So now we get to factor all over again. We would say, hey, I'm going to multiply through by a negative 1, so q squared plus 2q minus 596. Now, what two numbers multiply to make 596 that add to make 2? A little less obvious this time. So if you wanted to just say, hey, forget factoring, I'm just going to do the quadratic formula, you could. Or, can I show you all a really cool trick? A factor table is very helpful. I'll do the factor table for 99 because it's easy. When you do a factor table, you say, what goes into 99? You start counting at 1, 2, 3. So 1 goes into 99, 99 times 2 doesn't go into it, 3 goes into it 33 times, 4 doesn't go into it, 5 doesn't go into it, 6 doesn't go into it, 7 doesn't go into it, 8 doesn't go into it, 9 goes into it 11 times. And that's the end of my factor table. Wasn't very interesting. Those are the only things that go into 99. If I was about to do that for 596, I'd be here for a while. right? So 1 and 596, probably 2 and 298. And then you'd have to move on to 3. Does 3 go into it? No, thank goodness. Does 4 go into it? Yes, that would be 4 and 199. And it might be already almost done. No, I think something goes on 199. Okay, so everybody, how do you get a factor table on your iPhone? On your calculator. So everyone go to y equals. Go to y equals. And here's the beauty. You just type in 596 divided by x. 596 divided by x. And what we're going to do here is just start dividing 596 by every whole number. So now if you go to the table, so don't hit graph, right above graph says table, hit second graph, go to the table, and your table, provided it starts at 1, that is the factor table, but maybe your table didn't start at 1. You have to go to table set above window. So if you look at your window button, right above it says table set, so hit second window, and you say table start, I want to start my table, start at 1. And I want my delta table to also be 1. That means I'm going to input 1, 2, 3, 4. Now I go back to second graph table, and there's my factor table. You can see on your factor table, any output that comes up to be a whole number really is a factor. If it's a decimal, it's not a factor. So now you just scroll down until you find something that's not a decimal. Oh, I didn't find anything else that's not a decimal.
What was the equation that you did?
Just 596 over x. If you do y1 equals 596 over x, then that's going to give you a table, a factor table. But you know what, folks, so I just found is that nothing else goes into it. Yeah, it's only 1, 2, and 4. So what does that mean? Can we factor this problem? No. There are no 2 numbers that multiply to make 596 that add to make 2. So what does that mean we have to do? Yeah, you can do the quadratic formula, or you could do, if you like to do completing the square, you can do completing the square. You know what, just for fun, because you can do the quadratic formula, maybe I should show both. Completing the square right here might not be that bad, because you move the 596 over, and you say q squared plus 2q equals 596. And then in order to complete the square, remember what to do? You take half of the middle number and then square it, and you add it to both sides. So what's half of 2? Yeah, 1, and then you square it, and that makes 1. So you add 1 to both sides, and now q squared plus 2q plus 1 can be written as q plus 1 squared, and that's 597. I don't know that that helped us, because 597 is not square rootable. But that's okay, you know, we could get an answer that's a decimal. So now we square root both sides, and we get the square root of 597. Yep, it's just some crazy decimal. Q plus 1 equals 24.4335. And then you subtract 1 from both sides, and you get q equals 23.4335. What? So that was completing the square. I only showed it just, you know, in case that's what you like to do. You can always just do the quadratic formula. What would the quadratic formula look like? It would be q equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And then, so these are values for a, b, and c. So we have negative 2 plus or minus the square root of 2 squared minus 4 times 1 times 596 all over 2a. Okay, so now you have that monster to calculate. Let's just see if we get the same answer. 2 squared is 4 plus 4 times 596. So that's negative 2 plus or minus the square root of 2388 all over 2. And I'm going to square root that now. So that's negative 2 plus or minus 48.8671 all over 2. And if you do the quadratic formula, folks, remember you have 2 alternate realities at the end here. You're either going to do plus or you're going to do minus. So I have negative 2 plus 48.8671 all over 2. Or I have negative 2 minus 48.8671 all over 2. Do I have to bother calculating this one? Why not? We're not doing negative. Yeah, we don't need a negative value for q. But this one, if I go ahead now and finish, that plus negative 2 divided by 2, oh my goodness, 23.4335. Did we get the same answer? Yeah. I ran into a different digit, but Yeah, so whether you want to complete the square or quadratic formula, that's totally up to you. I think probably the easiest thing for us to do going forward is just do the quadratic formula. But if you wanted to complete in the square, that would be up to you. Okay, so then what does this problem, what did we find out? I think I turned the page. There we go. It was at what value of q does d of q cross the q axis? So at what value of q? 23.4336. Now what does that really mean? Remember, what is the unit for q? Q is in thousands, so we can actually move the decimal 3 times now. So that's really 23,433.6. So that's how many units you're actually selling. 23,000. And what does that mean? What would the price be at that moment? Yeah, free. This is hilarious, right? So you have this product, and you're saying, golly, how many of these products could I possibly get into society? How many people could I possibly get to show up? And the sad fact is that even if you gave it away for free, only 23,433 people would show up. Okay? So that 23,434th person would be like, whatever, I don't care that it's free. I'm not leaving the house today. I don't care if it's free. I don't want it. It's a piece of junk. Right? So the x-intercept is a really funny value. That is, how many people in society are even interested in your product if it was free? Right? That's interesting because now you know how many people are out there that would buy your product. And it's also sad because that tells you there are other people in your society who couldn't care less about your product. Josh?
Where does the equation come from? How do you form it?
No, I'm just kidding. It comes from data analysis. So what they do is they take polls and get data from people and just ask people, how many of these would you buy? Or they extrapolate. So on a given day, your store is selling these products. Like let's say you're selling TVs and the TV is set for $400. Then maybe they take 1 month worth of data and they say at the end of the month, 37 people bought the TV. And then next month, you know what they do? They put the TV on sale. They're like, hey, the TV's only $390 this month. And then they see how many people show up to buy the TV, let's say 40. And then they use these 2 pieces of data to extrapolate and say, there's my demand curve. Yeah, so again, it's not the mind of, it's not heaven telling you. It's just based on data and sample sales that you got. And then you extrapolate and say, well, if on this week, this is how many TVs I sold at these prices, then I can extrapolate and create a whole demand curve. Yeah, so it's all based on advertising and marketing and sales, past sales. Okay, well that was fun. But yeah, if you were a business owner, would you be really interested in having a demand curve for your product? Yeah, I mean, that seems pretty important. It would allow you to know what price you should charge to get that many people to show up. And it would also be interesting for you, like if you're manufacturing your own product, like you're making hand-carved wooden tables, then again, you could look at the formula and say, this is the lifestyle I want to live. I really only want to make 20 tables a week. How many people will I get to buy it? Is this really sustainable? Should I be in this build? Should I be in this business? There we go. All right, so number 8. And then what do we have? 7.
Yeah, number 7.
Can we skip to 8? I put number 8 next. I'm going to trust my brain that I put it next on purpose. Other than the idea that I just randomly put it out of order. I think I did it on purpose. Okay. So, number 8, I'll just tell you, is historically one of the more challenging problems I've seen in this, class. And what I really mean by that is that people have traditionally struggled with it. But it's not a hard problem. It's just long. Okay? It's just a longer problem. And in fact, it responds to exactly Josh's question. This is going to walk us through a data extrapolation process in which we build our own demand curve. Okay, so Josh, this is exactly what you would do if you wanted to build your own demand curve. All right? So let's look. A baseball team plays in a stadium that holds 52,000 spectators. Okay? That number is not really important. That's just the size of the stadium. But that does tell you the maximum number of people that you could have show up. Right? You're not going to let more than that number of people in because then it'd be a fire hazard and safety issues and people would trample each other. So with the ticket price at $12, the average attendance has been 23,000. So it's either telling us past sales, that if we set the price at 12, then the attendance is 23,000. So we could go ahead and start by making a graph. We know from our work so far that quantity goes here, and D of Q is our function, so price goes up here. And we're saying that with a price of $12, the attendance has been 23,000. Yeah. Now, what do you think, folks? Should we work in thousands, or should we just write down 23 and just remind ourselves that we're working in thousands? I mean, maybe we should just write down 23 and just remember that we're working in thousands. So I'm going to put my axis now, Q, in thousands. Okay, so now what? When the price dropped to $10, so for whatever reason, they put the tickets on sale. Okay, so put your coordinate there. At $12, 23,000 people showed up. At $10, what? The attendance rose to 26,000. So just imagine, this is all the baseball stadium has to go on. Like they're a new baseball stadium in town, they just built the stadium, they're wondering how much should we charge per ticket, you know, what's gonna be the most profitable way to do this. And so they take two pieces of data and they say, let's just go ahead and assume that's our demand curve. Let's assume this is our demand curve. You'll notice there's a big assumption. It says, find a demand function, D of Q, where Q is the quantity or number of spectators, and assume D of Q is linear. You know, that's a huge word. Another word, assume, right? And when you assume, you make an ass out of you and me. Have you all heard that one? You and me. You make an ass out of you and me. So we are assuming that this is linear. Didn't we already have a demand function that was quadratic? Yes, I mean, do we really know that it's linear? We don't know, right? Nobody knows. How would you find out if it was linear or quadratic? You would need a lot more points, wouldn't you? You would need to choose a huge sampling of points. You'd have to raise the price higher, lower the price lower, get a whole bunch of data points, and if your data looked like this, then you would say to yourself, okay, let's assume it's linear. But if you were taking all your data points and it looked more like that, then you'd say, okay, let's assume that it's quadratic. Right? So it all depends on the data that you're getting from your society. Okay, so in any case, there we go. This is what we have. Now we want to find a demand function, D of Q, that we are assuming is linear. So what we want, maybe make yourself a little 1 here, what we want is D of Q equals mx plus b. Right? We want some linear function, mx plus b. There's a variety of ways to come up with a formula, y equals mx plus b. I think the most concise way to do it is using point slope form. So again, a calculus class goes back to all of the math you've ever learned, like factoring quadratics, the quadratic formula, completing the square. And now point slope form, y minus y naught equals m times x minus x naught. So that's probably going to be our best way. In order to use point slope form, you're saying, assume you know a point, x naught, y naught, that the line is going through, and assume you know the slope. So do we know a point that our line is going through? Yeah, we know 2 points, actually. Do we know the slope of our line? Not yet, but we're about to. I like to find my slope visually. It's just so simple. So from this point to this point, I go down and then I go right. So I can go ahead and just visually say, my slope is down 2, right 3. And I'm already done. There's my slope, negative 2/3. If you want to, yeah, well, that's right, over 3,000. If you wanted to, you could do the actual slope formula, right? You could do, you know, what were our coordinates? 23, 12, and 26, 10. And then you could sit there and say m equals y2 minus y1 over x2 minus x1. And then you'd still end up with negative 2/3. So that part is up to you. I don't mind how you calculate the slope, just so long as your calculation is accurate, right? But you can do it visually or you can do the real slope formula. So now what do? We go ahead and plug everything in. You know I'm a big fan of writing things empty. I'm going to write y minus something equals something times x minus something. And now what do we plug in? Something. Very good. So I know my slope is negative 2/3. But now what coordinate do we want to use? Do you want to use the first coordinate they gave us, 23, 12, or do you want the second coordinate, 26, 10? Yeah, it doesn't matter, does it? You can choose either coordinate. So it's totally up to you. Which one did you want? The first one? Sure, you can use the first one. Let's do the first one. Remind yourself, this is x naught, this is y naught. So my y naught is 12, and my x naught is 23. And now I'm ready to go. So what do you do now? We want to simplify this down to y equals mx plus b. We will add 12 to both sides after we distribute the negative 2/3. So this will take a little bit of finesse here because negative 2/3 times x is easy. It's just negative 2/3 x. But now I'm going to do a negative times a negative, which is positive, and I'm doing 2/3 times 23. I'm going to go somewhere else and do 2/3 times 23, 23 over 1, multiply straight across. That's 46/3. 46/3, you can change that if you want to. You could say that that's 15.33333 repeating if you use your calculator. But just make sure you put that repeat bar because you want as much accuracy as possible. So now if we want to, we can call that 15.333 repeating. Did I do that right? It is 15.3. Yeah. And now we can add the 12 over. Right? So now we have y equals negative 2/3 x plus 27.3 repeating. And that is our demand function, where it's negative 2/3 q plus 27.3 repeating. And if we go back now to our original graph that we drew, where's my y-intercept? Where's my y-intercept? 27.3. Now what does that mean? This is funny. This is very funny. If I charge $27.33 per ticket, how many people will show up? No one. No one at all, right? You just priced yourself out of society. You're like, hey, everybody come to my baseball stadium. I charge $27.33 a ticket. No one will come. So the y-intercept is a hilarious concept because that's, if you charge more than that, no one will come. And then the x-intercept was also a hilarious concept because if you charge nothing, that's how many people would show up to get it for free. Yeah, so can we find that real quick, just for fun? In the context of this problem, again, the x-intercept means you have a value of q and y is 0. So I take this formula and I do what? Set it equal to 0. So now I have negative 2/3 q equals negative 27.3 repeating. And then I want to get rid of the negative 2/3, so I multiply both sides by negative 3/2. Right? You multiply by the reciprocal. So I'm going to multiply by negative 3/2. And therefore, my q-intercept, this is just for fun, we're just curious, negative 27.3 times 1.5 is 40, well, 40.99999, so we're going to call it 41. So what does that mean? Even if you charge nothing, if you charge nothing and say, hey, everybody, come to my free baseball game, how many people will show up? 41,000. And how large is your stadium? 52,000. How many more seats do you have than you'll ever be able to fill? 11,000 seats. You completely overbuilt the stadium, didn't you? So in this market, it makes no sense to have built a stadium that's 52,000 spectators. Because even if it's free, only 41,000 people would show up. So what would you have to do? If you were owning this baseball stadium, what would you do? Yeah, you would have to advertise to a whole new group of clients, right? Like go beyond baseball. You would need something to bring people more than the 41,000 people who would come for free. Okay, so folks, how do you feel about all this? This is interesting. Like, this is interesting. This whole notion of having a demand function, especially how you come up with a demand function. How did we come up with our demand function? Just 2 coordinates. That means 2 examples of prior sales. 2 examples of prior sales is enough to give you an idea of what your society is like and how many people will show up to buy your product. Ideally, though, if you're running a business, how many more coordinates of prior sales would you want? A lot. You would keep track of your sales every single month, right? And then that way, every single month, you can update your demand function and have a better idea of what price to charge to really work over the people in your society. I mean, to sell your quality product to the people in your society. Okay, wonderful. So I know my phone just went off. Let's just see here. We have 7 and then 9, and then that's it. Okay, well, I think a couple of these are really short problems. Let's just take a peek, and then we'll take a break, and then come back and do something completely different. So, now by the way, folks, again, what does the demand function actually calculate? Price. The magical price. Okay, so this one. Let the demand function for a product be given by that function, or Q is the quantity, and D is the price per item. There it is again. Who asked about price per thousands or price per item? It's always per item. That can be charged when Q units are sold, suppose fixed cost of production, or 2,000 variable cost of channel. Oh. Okay, we'll do this whole problem. Let's take a break. So time's 11:54. Let's all be back at 12:04. Take a break.
You're gonna attend the celebration of pie.
When is it?
This is March 6th.
Oh, of course. Let's see. March 6th is. Yeah, I'll be here. Geez, who would miss the celebration of pie?
They're doing something amphitheater.
Cool. It is, but we're on spring break. Yeah, it's a cruel joke to educational institutions everywhere that Pi Day always falls on spring break. It's like the one holiday you'd really want to celebrate as a school, and you're on break. Josh, good question about the, where does the demand function come from? Does that answer your question?
Yes.
Okay.
Last time I saw you talking about
My wife and I many years ago went on a trip through Southeast Asia where we went Vietnam, Thailand, Cambodia, India.
You said that, like, guys usually have your,
Oh yeah. The day we were getting on the plane, like we had our backpacks on our back. We're getting ready to get in the car, and I'm like, we don't need a visa? And I get online and check, you did need a visa. So we changed our flight to the next day, and that gave us time to order a visa. And then it was planned like this, that we'd fly into South Korea. The visa would be made available right then. We would print it, and then we would fly from Korea to Vietnam the next day, and then we'd have our visa. So instead of waiting all the way until we got the visa and then leaving the US, we left the US on the hope that this whole visa thing would really work out, that we could print it out in South Korea and then get to Vietnam. It worked, yeah. And so in South Korea, we had 10 hours till we just left our bags at the airport. We got on a bus and we'd go tour downtown South Korea for a few hours, and then we went back to the airport and we're on our merry way. Correct. Certain countries you don't need a visa. Yeah. Sure, yeah, it was wonderful. Yeah, you can just look up a list online. What countries you need. All right, folks, let's proceed. So, it says let the demand function for a product given by this demand function, where Q is the quantity of atoms in demand, and Q is the price per item. Now, from here, we're going to start building our own function. We're going to do a whole problem with this. So suppose the fixed cost of production are $2,000 and the variable costs are $2 per item. So let's go ahead and start right now and just find the cost function. And we have questions A, B, C. They have to do with revenue, costs, and profit. So let's go ahead and work on the cost function first. So it's saying that the cost for a given quantity is, the variable cost is $2 per item, and the fixed cost is $2,000. So this will often be the case that we just have a linear cost function. So that's pretty straightforward. If you want to know the total cost to produce 95 items, we just plug 95 into that, right? So you notice that the cost function has nothing to do with the demand function. The demand function is what price should you charge to get so many people to come out and buy your stuff. This is your cost. You know, how much it's going to cost you to build your product. So 2 times 95 plus 2,000, our cost is what, 2,190? Okay. So again, you'll notice that had nothing to do with the demand function, because the demand function had to do with the magical way of knowing if you charge this much money, this many people will show up. These are your own costs. Okay, now what about revenue? Revenue, as a function, revenue is always, by definition, price times quantity. This is worth memorizing. Revenue is always price times quantity, right? Assuming you're looking at one product at a time. Yeah.
Why do you use 2,000?
Why did I what?
Use 2. It says the fixed is 2,000 and variables 2,000. So
Yeah, the fixed is 2,000, so there's no variable there. And the variable cost is $2 per item, so it's 2 times Q. Because for every item that you produce, you're paying $2 for it. Well, that's the demand function. This is the demand function, which tells you what price you should charge to get so many people to show up. Yeah. Okay, but now we're about to go back to that. So revenue is price times quantity. That makes sense. If you're selling just pepperoni pizzas and you're selling them for $10 each, then the only question is $10 a piece. I sold 100. You multiply 10 times 100. So revenue is price times quantity. Now, price is determined by the demand function. This thing right there is the price. That's the price you're going to set, right? Because you're not just going to set the price willy-nilly. You're going to use the demand function to determine the price that you charge. So what we do right here is we insert the entire function for price. So the entire function now is negative 1.95 Q plus 240. And then you're multiplying that times quantity. So now that becomes your revenue. Revenue is always price times quantity. And we can clean that up a little bit by distributing the Q. And now we have negative 1.95 Q squared plus 240 Q. So that's actually our revenue function. If you want to look at what that graph would look like, it's an upside down parabola. And I believe it looks something like that. Of course, we can always just graph it to find out. So that's our revenue. Now they are asking us to find the total revenue from selling 95 items. So we would go ahead and plug in R of 95 equals negative 1.95 times something squared equals 240 times something. So let's go ahead and find out what that revenue will be. So if we sell 95 items, and allow your brain to think about what just happened. We're saying that we want to sell 95 items. So if we only want to sell 95 items, and exactly 95 items, then that demand function is going to tell us what price to charge to sell exactly 95 items. And we're plugging that price for selling 95 items, and then we're going to multiply it times the 95 items that we're selling. And so what do we get? From our calculator, negative 1.95 times 95 squared plus 240 times 95. $5,201.25. So far, how are we feeling about this business? We just brought in $5,000. It only cost us $2,000. This is good business.
right? We should all be very happy with that. Now, the total profits to produce those 95 items. So profit, we know, is profit as a function of Q is revenue minus cost. Now, at this point, I know that the easy thing would be to just go ahead and plug in those numbers, right? You can just say 5201.25 minus 2190, and that's immediately going to tell us what our profit was. And that's a perfectly valid point. That if you just wanted to know the profit, you just subtract those two numbers, and it's 3011.25. That's a goodly amount of profit. Especially since, we're kind of assuming the $2,000 paid for everything. Rent, electricity, air conditioning, employees, right? So I mean, what's that?
All that on $2,000.
All that on $2,000. I mean, that could be your cost for one day. You never know. It could be the cost for one day. Okay, so we made $3,000 of profit. But what we really want is also the formula itself. So the formula itself would be our revenue formula, negative 1.95 Q squared plus 240Q, minus our cost formula, which was 2Q plus 2,000. And so we have to distribute that minus, and then what do we have? Negative 1.95 Q squared plus 238Q minus 2,000. Okay, even though in this particular case, it was easy enough to just subtract those two numbers and just find out the profit, we do want to have a profit formula that we can use for future reference. So now in this particular business, we have a revenue formula, we have a cost formula, and we have a profit formula.
So which one are you expecting us to use?
All three. You'd want to be able to talk about all three things.
For that last one, like, we do that.
Oh, the question might say find the profit formula, and then that would be this. The question might say find the profit for 95 items, and then the answer would be that. And by the way, you should all convince yourselves, if I plug 95 into this formula, is it going to give me the same answer?
Yeah.
Yeah, I mean, it better. If it doesn't, that means we made a mistake somewhere. Negative 1.95 times 95 squared plus 238 times 95 minus 2,000. And sure enough, it gave me the same answer, 2011 and 25. Yeah, so thank you, Sarah. The instructions on the test will tell you which one you're supposed to be doing. But as a general rule, I would always come up with the general formulas first, and then I would plug in 95. That way you're doing it both. Okay, well, there we have it. Now, getting all the way to the profit formula is really what we're interested in, right? I mean, is that oftentimes the bottom line for a company is, so what was it? Negative 1.15 x squared plus 2x. Oh, it's 95? What do I have to fix? Okay, there you go. So everyone take a look. Here's my function. So based on that, what do we want to do? We want to maximize our profit. So how many items should we sell?
61.
61. If we sold 61 items, then we're going to maximize our profit at 5,262. And do we have any reason at all to make more than 61 items? I mean, unless you have other goals. If your goal is to be really well known and to be the only product people are buying. Like if you're, Papa John's and all you have to do is sell 61 pizzas and you're good. But maybe what your goal is to get everybody to buy Papa John's. You want to dominate Domino's and Little Caesars. Then maybe that's your goal. You're like, forget profit. I want to have the largest market share. Well, then that would be a very different consideration, right? So it all depends on the goal of your company. Sometimes people will allow their profit to be less because that means they're having a larger share of the market. And maybe that's what they really want, is to be like well known. Okay. All right, so what do we have? I hope just one more question, and then we're going to start talking about. Is it number 9 now? Okay, good. Last one. What? There's no 10, right? Okay, good. Okay, the total cost to produce 2 units of goods is given by the cost function. What is the total cost? And what is the cost of the 800 first item? We won't even, I'm just going to set it up. You can finish the calculation on your own. How do you find the total cost?
Just plug it in. How do you know that you're plugging it in? Yeah, you replace Q. You think about the units, right? Q is quantity, whereas C is cost in dollars. And they're telling us Q equals 800. By units alone, you know that you're plugging it in for Q, because it says Q. And so you're not setting it equal to 800, you're plugging in 800. And then finally, what is the cost of the 801st item? So how do you find the cost of just the 801st item? You find the cost of 801 items, all of them, all 801, and then you subtract out the cost of the first 800 items. And that is the cost of the 801st item alone. All right, well, I think that was good. That was a nice discussion about the demand function. We're going to use the demand function again and again in class. And you'll notice, did we do any calculus in that section? None at all. We didn't do a derivative. We talked about marginal cost. Like this is the marginal cost of the 801st item. And we talked about finding slope, but we didn't actually do any calculus. So now what we're going to do is talk about shortcuts. A shortcut is very helpful. So here's what I'm going to do. We're going to walk our way through these notes. And please stop me at any time and ask questions. Everybody ready? Boy, like 7 of you are writing. That's fine. I'll give you a second if you're writing things. Does anyone have any questions you want to ask? No? You're all just happily writing along? I think that's fine. That's fine. Okay, so let's start at the top. Mathematician, that's you. So the power rule, finding the derivative of any polynomial function f of x equals x to the n. That's our goal. Is that if I said to you, hey, your function is x squared, what's the derivative of that function? It's 2x. And if I said, hey, f of x is x cubed, what's the derivative of that function? And I would like you to be able to say it off the top of your head. If I said, your function is f of x equals x to the 4th, what's the derivative of that function? And you'd be able to say it off the top of your head. Up until this moment, the only way we know how to find a derivative is to do this terrible process of the limit as h approaches 0 of f of x plus h minus f of x all over h. But you will be able to do it in your head by the time we're done talking right now. So let's just review some concepts. The average rate of change is the slope between 2 points. That's what we call the average rate of change. And a line drawn through 2 points is called a secant curve. Whereas the instantaneous rate of change is the slope at 1 point. And a line touching the curve at 1 point is called a tangent curve. Right, so this is, again, this thing right here is pre-calculus. And this thing right here is calculus. Our goal is to find the slope at a point. Calculus finds the slope of a tangent line by finding the slope between 2 points that are infinitely close. And infinitely close is what the limit as h approaches 0 means. H is the distance between the 2 points. And if the distance between the 2 points approaches 0, they become infinitely close. So again, the function f of x tells you the height or the y value, whereas the derivative f prime of x tells you the slope at that point. Okay. So I'm going to go ahead and give you some functions, and you're going to guess the rule. So if we had a linear function like mx plus b, which again is just a line, right? What is the slope at any point on a linear function? What's the slope at this point? What's the slope at this point? What's the slope at this point? What is it? Just that. Yeah, the mx term is telling you the slope, but m is the actual value of the slope, right? So if you did the derivative of mx plus b, the derivative would just be m. That's the answer. The derivative of mx plus b is m. Meaning if you did this whole process using
mx plus b, your final result would just be n. That would be an interesting exercise for you to go home and try on your own. You know, do this whole limit process with mx plus b as your function. You could do it. Okay, now what about the parabola? When f of x was x squared, we already did f prime of x, it was 2x. Now I'm going to give you some data, and you're going to come up with a rule. So once you see the rule, don't just shout it out. Let's let everyone have a chance to find it. If you have the cubic function, the derivative is 3x squared. Now again, you can do that whole process. You could go home tonight for funsies, and do this process with x cubed. You could do it. You could, do x plus h cubed minus x cubed. Foil the whole thing out, and you'd get the answer of 3x squared. What about the quartic function? So x to the fourth. The derivative there is 4x cubed. And again, you could go home and do that tonight for funsies. You could do the function x to the fourth, do this whole definition. After all that algebra that gets worse and then gets better, you would end up with the answer 4x cubed. Okay, so do you see the pattern? And to tell you the truth, you might not want to look at this one too much, because those make it a lot more obvious, although you can still see it. The m x to the 1 right there, and put that as x to the 0. Right? You can still see it. So what is happening? What do you do to this function to get to this function? Or better yet, just what do you do to drop down from one line to the next? What are you doing? Nanda?
You multiply by the exponent and subtract 1.
That's exactly the rule. You multiply by the exponent, and then you subtract 1 from the exponent. Is there a spot to write that down? There's not. Verbalize it. Verbalize it. You would multiply by the exponent, and subtract 1 from the exponent. Yeah, that's exactly right. Did that work all the way across? You multiplied by 2 and then subtracted 1. You multiplied by 3 and then subtracted 1. You multiplied by 4 and then subtracted 1. So what about the general power rule? What if you just have x to the power of n? Write down your guess of what that should look like. You just had x to some power. Multiply by the exponent, then subtract 1 from the exponent. What would your answer be?
N.
Yeah, n times x to the n minus 1. And that right there is called the power rule. So in differential calculus, we call this the power rule. The power rule states, now first of all, that sounds exciting, like the power rule, like we're talking about He-Man or She-Ra, or maybe we're talking about politics, the power rule. But no, in this case, we're just talking about a power function. It's a power function, and this is the rule for power functions, that if you have a variable to a power, you just multiply by the power, then subtract 1 from the power, and that's it. That's the derivative. So given any power function, this is just a summary, f of x equals x to the power of n, then the derivative is f prime of x equals n times x to the n minus 1. Now what I haven't done for you is actually prove that and derive that. We didn't go through a whole proof. Doing a whole proof would probably only take like 10 minutes. But 10 minutes I feel like we don't have. And the real question would be, would you like to see it? You know what I could do is I could write it down on a line sheet of paper and then I could just post it. And then if you're interested, you could go look at the proof. Because it's pretty interesting. It's pretty straightforward. But what I really want to see all of you do, I want to see you go home and try the cubic and try that quartic. Try that out using this formula. Just try it out on your own. And then I'll post for you the answer for x to the n. Because it is a neat looking proof. Okay, so everybody ready? We're going to try this out. So our power rule is multiply, subtract 1. Multiply, subtract 1. And in fact, that's still worth writing down. Multiply, subtract 1. First, you have to know what that's referring to, right? You're multiplying by the exponent, and then you're subtracting 1 from the exponent. So the general rule is multiply, subtract 1. Multiply, subtract 1. And so part of why I gave you this sheet is to build some muscle memory. You all know the word muscle memory? Muscle memory, it's just, bam, you can just do it. No need to think. It just happens automatically.
And muscle memory means that that memory is in your muscle. Whether that muscle is your tongue or your hand, you just build that muscle memory right in. So, there we go. So, we already know that the derivative, so multiply by 2, subtract 1. Multiply by 3, subtract 1. Multiply by 4, subtract 1. So now, I'm going to go around the room. So we'll start with you, Sarah. Tell me what to do. Yeah. And actually, you can just tell me what the answer is. How about that? You can just tell me the answer. Fatima? So it's 6x to the 5th? I'm sorry, I think I cut you off. Fatima, try it again. 2x to the 7th.
7x. I mean 6.
Yeah, 7x to the 6th. Very good. You don't have to say the minus part, but yeah, 7x to the 6th. Okay, Molly?
8x 7.
Yeah, 8x to the 7th. Very good. Who's that?
9x to 8.
Yeah, 9x to the 8th. Henry? 10x. Very good. And then Holly?
11x to the 10.
And Josh?
12x.
Yeah, very good. And Nanda? 13x. Very good. And then Jared?
14x to the 13th.
Very good. Everyone just finish that row. We have 2 more there. I do recommend you write them all down because it's good muscle memory for your hand. You get in the process. It's almost like you feel yourself bringing the exponent down and subtracting. Bring the exponent down and subtracting. Okay, now what's really cool about the exponent rule is that it works even when the exponent is not a positive number. So let's take a look at just x. Like just x. Keep in mind, this is just x. Just little old x just sitting there. What happens when we bring the 1 down and then subtract 1? What's x to the 0? Well, it's just 1. So the derivative of x is just 1. Okay, it even works when the exponent is 0. So you bring the 0 down, 0, x to the 0 minus 1 is negative 1. Well, it doesn't matter what x to the negative 1 is. 0 times anything is 0. And x to the 1 is really 1. So what we've learned here is that the derivative of a constant is nothing. The derivative of any number is just 0. Okay, keep going. What about x to the negative 1? You bring the negative 1 out front, and then subtract 1. Negative 1 minus 1 is negative 2. Now, before we move on from there, let's remember our exponent rules. Anytime you have an exponent to when you have a base to a negative exponent, you push that base down into the denominator and make it a positive exponent. So remember that rule? So we wouldn't just leave our answer like that. We would write our answer as negative 1 over x squared. Because we have a standing order from mathematical society that we never leave our answer with a negative exponent. So likewise, in the next one, I bring down the negative 2, subtract 1, that's negative 3. Now, I'm not trying to do all that in my head and immediately push the x down below. That'd be too much to do in your head. Now that I wrote it down, I would rewrite it as negative 2 over x cubed. And again, for the next one, I bring down the negative 3, I subtract 1, that's negative 4, and then I would rewrite it as negative 3 over x to the 4th. Now, I really want you to appreciate what we just got out of this formula. The fact that it refers to any exponent, because really, think about what this function would look like. F of x equals 1 over x cubed. That would mean that I'd have to do the limit as h approaches 0 of 1 over x plus h cubed minus 1 over x cubed all over h. Who wants to do that? Nobody wants to do that. What would you have to do? You'd have to find a common denominator. You have to multiply top and bottom by x cubed over here. Multiply top and bottom by x plus h cubed over here. I can't even write it. There we go. And then once you have a common denominator, you would need to do x cubed minus x plus h cubed all over the x cubed, x plus h cubed, all over h. And then I would still have to FOIL x plus h cubed out. Oh my gosh. That would end up looking like x cubed minus, and then you would have x cubed plus 3x squared h plus 3xh squared plus h cubed. Okay, now all of that is over x cubed, x plus h cubed, all over h, right? So this is if you were doing the whole limit definition. Then I'd have to distribute that minus sign to subtract all of those. The x cubes would cancel out, thankfully. And then I'd have negative 3x squared h plus negative 3xh squared minus h cubed all over the x cubed and the x plus h cubed. And then all over h, I'm just going to put that h right there now. Since I'm dividing by h, I can just put it in the denominator.
Then I'd have to factor an h out of all the top, so then I'd have an h over negative 3x squared minus 3xh minus h squared, all over the h and the x cubed and the x plus h cubed. Then the h's finally cancel out. And then what? Now we can finally do the limit as h approaches 0. In the expression negative 3x squared minus 3xh minus h squared, all over x cubed times x plus h cubed. So now what can I do? Now I can plug 0 in for h, right? So that term goes away, that term goes away, this h goes away. And now we have, I'll come back closer to you, negative 3x squared over x cubed times x cubed, which is x to the 6th. And then the 2 of the x's cancel out from 2 of the x's on the bottom. We have negative 3 over x to the 4th. And was that the answer? Negative 3 over x to the 4th? This way was faster, right? A lot faster. So that's another reason why this thing is called the power rule. Like, it's a double meaning, right? Like, it's not just how you deal with an x to a power, but it's like powerful, right? You get to skip all that work. You never have to do any of that work again. It's really cool. Okay, so you're all impressed, right? That it's a huge time savings. You never have to do that method again. We can just use the power rule. So now these are ones that you want to memorize right here. These are special ones. So if you just have x, okay, just regular old x, then you bring the 1 down, x to the 0, that's just 1. So what is the derivative of x always? 1. Just 1. The derivative of a variable is just 1. So that's nice. What if the variable has a number in front of it, like mx? Then in that case, the 1 would come down, that's 1 times m times x to the 0. The x to the 0 is just 1, so that's really just m. Now what that tells us is that anytime you have any number x, the derivative is just the number. So for instance, the derivative of 5x is just 5. Right? That's very helpful and quick and easy. What about the derivative of a number? We already said what the derivative of a number is. The derivative of a number is 0. Prove it to yourself. This is really 3x to the 0. And if you bring the 0 down, that's 0 times 3 times x to the negative 1. It doesn't even matter what x to the negative 1 is, because 0 times anything is 0. And so that tells us that the derivative of any number is just 0. And that's what this last one here is to remind you. That if your function is any constant number, the derivative of any number is 0. So there are certain things that now we expect you to just memorize. You just memorize it. So if I were to write down a real quick little cheat sheet, my cheat sheet would look like this. That if f of x is a number, then that derivative is just 0. And if f of x is a number times x, then the derivative is just the number. Whereas if the function is a power function, like x to the n, then the derivative is nx to the n minus 1. Those are 3 fairly good examples to know off the top of your head. Right? So that you no longer have to think about it, you just write down the answer.
How would you, what would root 2 and 3 look like to get there? So like mx to power n.
Oh, okay, sure. If your function was a mixture, like mx to the n, you can do that. Multiply by the n. So it's going to be n times n. It'll just be that. And that's a very important rule. What you learn is that any coefficient out in front just comes along for the ride. But if you have a coefficient in front of a power rule, it just comes along for the ride and it's still there. Yeah. All right. So we have a variety of power rule examples that I'm doing with you here so that you can see that the power rule works no matter what. No matter what power x to the anything, you can always use the power rule. So let's do a couple more examples to see that. If you flip to the next page, right? Josh, you guessed the next one I was about to do. So what if you have a constant out in front? If you have a constant out in front, then that constant just comes along for the ride. You still just multiply by n and then subtract 1. So the c is still there. So for instance here, if there's a constant out in front, it just becomes part of the multiplication problem. So
Here I multiply by 2, so that's 6x to the subtract 1, 6x to the 1. Or here, 2 times 5 is 10, and then subtract 1, 10x to the 1. Now again, in your head, you're still thinking multiply, subtract 1, multiply, subtract 1. So I'm going to ask you folks to do something. So I'll start with you this time, JR. Tell me, what's the derivative of 7x cubed?
21x squared.
Perfect, 21x squared. And now know what's your derivative of 10x to the 4th?
40x cubed.
Yeah, 40x cubed. And Josh, the derivative of 100x to the 5th?
500x squared.
Yeah, very good. Now, this is true even if the power function has a negative constant out front. So obviously, if you have a negative number out front, you still just multiply. So keep going, Colleen. Derivative of negative 4x squared?
Or no, then negative 16.
Remember, you're just going to multiply. You multiply.
Oh, 8, I'm sorry.
Yeah, negative 8. Yeah, x to the 1. Very good. And Henry?
You can do 16x to the 7.
Yeah, perfect. And what was that? Sorry, I went before you. Oh, and you were just saying x. Yeah, very good. You don't even have to bother saying x to the 1, right? You can just say x. Very good, Rosa. And then the next one there, Molly? Yeah, negative 5x to the 6.
Yeah.
So you multiply by the 6. Yeah, negative 30. And then x to the? Yes, very good. And Fatima? Yeah, negative 1,000 x to the 4th. Okay, now this is true even if the power function has a decimal exponent. This is trippy. So even if the exponent is a decimal, you can still just multiply by the decimal and then subtract 1 from the decimal. So you got to be really careful here. So 2.3 times 10 is 23, and then 2.3 minus 1 is 1.3. But that still is the derivative. Multiply, subtract 1, multiply, subtract 1. So Sarah, the next one? 7.5 times 2? 15. X to the 6.5. Very good. And the next one there, JR? Now, I realize you might need your calculators out for this. I don't expect you to be able to multiply all these decimals in your head.
340x to the 2.4 squared.
Yeah, very good.
2.4 power.
Yeah, just 2.4. Very good. Very good. Nando?
Negative 47.5x.
Yeah, negative 47.5x to the 8.5. Yeah, again, for us, you definitely need a calculator out to do this. Josh?
6, negative 660x to the power of 2.4.
Yeah, very good. Yeah, perfect, folks. Power rule always works the same. Multiply, subtract 1. Multiply, subtract 1. Now again, just imagine if you had to have done all these problems using this technique. I mean, you'd be here all day, right? You'd be there all day long. So we have a couple more here. This is true even if the exponent is negative. Now, when the exponent is negative, you have to be extra careful because when you subtract 1 from a negative number, the number increases in size, not decreases in size, right? So like this one, if I multiply by the negative 3, 4 times negative 3 is negative 12. And then subtracting 1 from negative 3 minus 1 is negative 4. And again, at this point, we're not done. You have to rewrite that as negative 12 over x to the 4th. All right, because anytime you have a negative exponent, you push that base into the opposite side of the fraction. Again, here it is. X to the negative n is really 1 over x to the n. So my x to the negative 4 gets pushed into the denominator. And that's just the language I'm going to use, is push. Right? If you have a negative exponent, push it into the other side of the fraction. Sarah?
So you could think of it like numbers.
Yes, you could think of that. The two numbers you multiply, so negative 3 times 4 go in the numerator, and then when you subtract 1, it goes down to the denominator. I would still recommend you do it in 2 steps, as opposed to just writing down the final step. Like, that would really make me nervous, Sarah. Like, if you just said, hey, 2x to the negative 2, that's negative 4 over x cubed. Ooh, that's a little too much all at once. You know, I mean, if you feel comfortable doing that, you can try it. But I would recommend 2 steps, okay? So that'd be negative 2 times 2 is negative 4, subtract 1, negative 3. Really, folks, I really recommend you do it in 2 steps. Now you rewrite it as negative 4 over x cubed. Okay, let's see here. Henry? Derivative of negative 12x to the negative 5th?
60 over x to the 6th.
Well, it's 60x to the negative 6, and then you're right. You would end up writing 60 over x to the positive 6. Yeah, very good. And then, was it?
Negative 20x.
Negative 5
I
times
mean,
negative 4.
20x.
Yeah, 20x to the negative 5th, which becomes
20x over x 5.
20 over x to the 5th. Yeah, there you go. Okay, let's see, Colleen.
That's 2,000.
Negative 2,000.
2,000, that's 2, negative 11.
Yeah, very good. And then?
It's 2,000, make 2,000.
Yeah, very good. Yeah, even more reason to do it in 2 steps. That was great, Colleen. Is you get to watch that negative exponent becoming a positive exponent. It's very important for your own brain and for your audience. You take that 1 step at a time. Okay, now this next one is even more tricky. It's true even if the power function has a fractional exponent. Right? So now we have 4x to the 3 halves. Right. Now again, how many people in society are really comfortable just feeling like, sure, 4 times 3 halves is 6. Like that's really not something we're trained to do all in our head. So you would use a little bit of scratch paper or type it into your calculator. So if I'm going to do 4 times 3 halves, I would use scratch paper and say 4 over 1 times 3 over 2. And at that point, you can just do traditional fractions where you multiply the top, multiply the bottoms, and then simplify. Or you can always cross-cancel. The 4 and the 2 are both divisible by 2, so I call that a 1 and call that a 2. And then I see 2 times 3 is 6, and 1 times 1 is 1. However you do it, I highly recommend you do scratch work and then come back and write your answer. So 3 halves times 4 is 6. And now what do? I want to subtract 1 from 3 halves. Now, 3 halves minus 1, when you subtract fractions, what do you need? You need to make it a fraction, first of all, so that's really 1 over 1. But you need a common denominator. The brilliance here, since we're talking about the number 1, you can write 1 in any way you like. It could be 5 over 5, 7 over 7, 10 over 10. So might as well be 2 over 2. So from now on, when you have a fractional exponent and you want to subtract 1, you can just immediately, don't write minus 1, just write minus 2 halves. Right? Because you know that you want a common denominator, so you can write 1 as 2 over 2. And that will help you see that 3 halves minus 2 halves is 1 half. So that's a lot going on. Still better than doing it this way. Right? Nobody ever wants to do that way again. So you have to be very, very careful and cautious. One more thing. You have this rule right here, that a negative exponent gets pushed into the denominator. What's the definition of x to the 1 half? It's the square root of x. Yeah, x to the 1 half is really the square root of x. So our final answer here is really 6 root x. The 6 is outside the square root, yeah. Now again, this class is subtitled Advanced Techniques for Algebraic Manipulation and Cancellation, right? We're bringing back all the rules you ever learned in your whole life in order to make nice, clean answers. So how about this one, 2x to the 4 halves? I would start by doing some scratch work. I'd say 2 times 4 halves, cancel the 2's, that's just 4. So I know that my product is 4. And then I'm going to subtract 4 halves minus 1, but I'm going to write 1 as 2 halves. So 4 halves minus 2 halves is 2 halves, and 2 halves is really 1, and I don't even have to write down the 1. So the answer is 4 halves. Of course, what is 4 halves in the first place? That's just 2. So it's really, that was just 2x squared in disguise as a fraction. So again, the answer is 2 times 2 is 4, subtract 1 is just 4x. Okay, so now how about this, 7/3. Again, you need some scratch work space. So you'd say negative 12 over 1 times 7/3. And I really recommend that you get back into the habit of cross-canceling. So 3 goes into 12 how many times? 4 times. So it's really negative 4 times 7. It's really negative 28. So multiplying 12 times 7/3 is negative 28, x to the, now this is 7/3. We want to subtract 1, but how am I going to write 1? 3/3. So now this is really to the 4/3. Negative 28x to the 4/3. I can't believe class is already almost over. So sad. Anyway, we'll be able to finish this in 5 minutes, and we're right on track for where I wanted us to be. Okay, negative 5 times 9/5. So again, negative 5/1 times 9/5. The 5's cancel out completely, and you just have negative 9.
Question.
Yes?
Don't we rewrite that x to the power of that fraction?
Good point. Thank you, Josh. If you have only x to the 1/2, am I going to ask you to rewrite it as a square root? Because that's polite society. Most people in society understand what a square root is, so that's nice to convert it to a square root instead of x to the 1/2. But 4/3, that's terrible. If you actually do the proper algebraic simplification there, that's really the cube root of x to the 4th. I see no benefit to that. Right? I mean, that's just as bad, if not worse, than just leaving it as 4/3, right? So thank you, Josh, for pointing that out. I will only ask you to simplify x to the 1/2 to be polite to your audience because people know what square roots are. But any other fractional exponent, you can just leave. Yeah. Okay, so then here, 9/5 minus 1 is really 9/5 minus 5/5, so that's really 4/5. Which again, thank you, Josh, you can just leave that. Okay, 200 times 13 to the 4th, or 13/4. I hope I've sold you on this whole scratch work stuff. Like, a lot of things you can do scratch work on a little corner of your paper. Okay, 4 goes into 250 times, 50 times 13, some big number. 650, great. So we have 650, x to the 13/4 minus 1 is minus 4/4. So 13/4 minus 4/4 is 9/4, so there you go. 650x to the 9/4. And finally, this is a really interesting case. The power rule even works if the fractional exponent, when you subtract 1, the exponent will become negative. So in this case, 1/2 times 4, we can all do half of 4 in our head. Half of 4 is 2. And then we're going to do 1/2 minus 2/2. Again, minus 1, but I write 1 as 2/2. 1/2 minus 2/2 is negative 1/2. Right? Now watch closely, because this one gets simplified a lot. Negative 1/2. First of all, what does the negative tell you to do? Yeah, push it down to the denominator. What does the 1/2 tell you to do? Rewrite it as a square root. So what happens here? If you do one step at a time, this becomes 2 over x to the positive 1/2. But then that's really 2 over the square root of x. That is a very clean answer. That looks really good. That's called final form. Right? If you were presenting that to your boss or to your company, saying, hey, this is our demand function, that's how you would write it, 2 over the square root of x. So some more tricky ones. 2 times 1/3. So 2 times 1/3 is simply 2/3. So our coefficient out front is just 2/3. X to the, and then you subtract 1, which really means subtract 3/3. So 1/3 minus 3/3 is negative 2/3. Now, Josh just asked, do you have to rewrite 2/3? No, but it is a negative, and so you do need to push. You have to push it down into the denominator. And what we have now this is even more tricky. We already have a 2/3. Therefore, we already have a fraction with a numerator and a denominator. Where does the x to the negative 2/3 go? Into the denominator with the 3. So that's what your answer would look like. It would actually be 2 over 3x to the 2/3. Again, this is tricky. This is subtle. We're talking about a lot of simplification rules, which you might feel like, oh, geez, this is just a bunch of rules. But they're important because it's how anyone else in mathematical society would expect to see the answer. Okay, we probably just have time for one more here. Negative 12 over 1 times 1/4. So 4 goes into 12 3 times. That's just negative 3. And then x to the 1/4 minus 1 is 1/4 minus 4/4. So that's negative 3/4. So again, what happens? This now becomes negative 3 over x to the positive 3/4. Okay. We can skip those last two. These are all just examples to give us muscle memory for this process. The very last page says that it works even if it's a polynomial. So I'll just do one with you real quick, or a couple that is, because I know you're probably ready to go. So even if it's a polynomial, let's just do that first polynomial and we'll pick up from here next time. To take the derivative of a polynomial, you just take the derivative term by term by term by term. So the derivative of 2x to the fourth is 8x cubed. And the derivative of 3x cubed is 9x squared. And the derivative of 7x squared is 14x to the first. And the derivative of 5x, okay, these last two are special cases, remember. The derivative of anything x is just a number. So the derivative of 5x is just 5. And the derivative of a number is just 0. So you don't even write plus 0. Anyway, that's it. So you'd say that's the derivative. All right. Well, folks, I'm very, very happy. Thank you so much. We've covered a good amount of material. You've created some space in your brain for this new idea of a demand function and how to use it. You've got the power rule down, multiply, subtract by 1. And when we all come back on Thursday, that's when we'll move in. We'll do the practice problems from 2.5a, which I have right here. And that's it. If you have any questions at all right now, or my office hours, you can feel free to come on up. Again, everyone go home tonight and try using the limit definition for x to the third and x to the fourth. See if you can derive that derivative on your own without the power rule. And I will send you the solution for x to the n.